Alright, guys, we're going to be solving those 5 long questions on unfamiliar functions and calculus to prepare you for your Unit 9 test on next Friday. Number 1, we need to sketch the graph of this exponential function y equals 2 to the x. The domain's given from -2 to +3. I've decided to set up my graph with an x width of 10 centimeters. I can see that my total width from -2 to 3 is 5 units. And so I've just decided to make each unit worth 2 centimeters wide. And I kind of did something, a little bit of work ahead of time. I know what the shape of an exponential curve is. Y equals 2 to the x, of course, going to look like one of these guys, isn't it? It's exponential growth because the base is greater than 1. And so I calculated what my endpoints were going to be. And so I typed in my left endpoint of -2. If I do y equals 2 to the -2, which is 1 over 2 to the +2, I get 1/4. And if I do y equals 2 to the power of +3, I of course get 8. And so I knew that I needed to extend from around, say, 0 up to, say, 8. And so I've got to have at least that height. So I also looked ahead on the question and saw that I was going to have to be graphing this quadratic on the exact same axes. That means it's got the same domain. So I put in the endpoints into the quadratic as well, just so I could kind of figure out how I was going to set up my axes. And so I had y was equal to 3 plus 2 times -2 minus -2 squared. And that gives me -5. And I had my right endpoint of +3. And that gave me a y value of 0. So the overall result then is that I need to extend my y-axis from -5 up to +8. Those are the extremes at my endpoints. That's a total of 13 units, which is why I've set my graph to be 13 units tall. It's got to go all the way down to -5, -4, -3, -2, -1. Here's my 0, so this is my x-axis. And it goes all the way up to +8. And then my y-axis, if this is at -2, -1, well, my resolution isn't great here, but I think that puts my y-axis right here. Okay, so there's -1, 1, 2, 3. And now my axes are just about set up. It doesn't matter if you label your y-axis all the way over to the left or on the y-axis itself. Alright, it's a little more conventional, isn't it, to put it on the y-axis itself, so I'm going to move mine over. So my 8 and my -5, let's put them all the way over here. 8, 4, and I'm going all the way down to -5. You know the IBs, they throw a hissy fit if you don't put your labels in. So don't ever draw a graph without labeling your axes. That's a sure way to lose a point. Always label your axes, if nothing else. And now we're finally ready to sketch the graph. I'm going to use my calculator to assist me here. I'm going to put into y equals 2 to the power of x. And then I'm going to look at the table, second graph. And that gives me a whole bunch of useful values. Let me just back up a little bit, and now I can see what all of my y-coordinates are for my x values extending from -2 down to +3. And so I can put all of those values onto my graph. I've got -2 I've got -1.5. I've got 0, 1. I've got 1, 2. I've got 2, 4. Oops. 2, 4, and I've got 3, 8. And let's draw the smoothest curve we can through those points, and we'll label it. This is the function y equals 2 to the x. We need to indicate where the curve intersects the y-axis. That obviously is right here. A good indication is an actual set of coordinates. That is the coordinate 0, 1. Let's do part B. We'll write down the equation of the asymptote. I hope you remember that exponential functions have got asymptotes that are horizontal, and because we haven't shifted this one up or down, then the horizontal asymptote occurs right on the x-axis. So here's my horizontal asymptote, and its equation is y equals 0. Remember, all horizontal lines, their equation is y equals something, and all vertical asymptotes or lines, their equations are x equals whatever the number is. But you must express asymptotes as full equations, not simply as numbers. Part C. Let's now put in a second graph. Something clever you can do on your calculator if you only want to look at one graph at a time is you can move your cursor over to the equals sign and then hit enter, and that deselects it. You'll see that that equals is no longer highlighted, which means it will not appear. It's like effectively being muted. And let's put in a brand new function, 3 plus 2x minus x squared. Alright, you see that this equals sign is highlighted, which means it will appear on the graph. Actually, I shouldn't be bothering with a graph. That gives me an approximate picture, doesn't it? But I think in this situation, because I'm doing the graphing, why don't we look at the table? And that will give us all the sets of coordinates that we need to put in. And so I've got negative 2 comma negative 5, negative 1 comma 0, got 0 comma 3, got 1 comma 4, 2 comma 3, and 3 comma 0. And we'll draw a nice smooth curve through this new set of points. And let's label this function. Y is equal to 3 plus 2x minus x squared. We need to indicate where this curve intersects the x-axis and the y-axis. Well, I think it's pretty clear that it happens right here. Let me put in the coordinates, negative 1 comma 0. And over here, the other x-intercept, is 3 comma 0. And then the y-intercept, I think you can see, is 0 comma 2. And now we've labeled all of the asymptotes, the intercepts. Let's move on to part D. Using the graphic display calculator, let's solve the equation. You'll notice that the first function that appears is the same quadratic we've already graphed, and this is the same exponential function we've already graphed. If we want to solve this equation, we're effectively trying to find out then, where do these two functions cross? So let me bring this one back into display by reselecting the equal sign, and now we'll go to the graph. And we can see that they intersect in two different places. Let's find those intersection points with second trace intersect. The first curve is indeed 2 to the x. The second curve is the quadratic. I'm going to guess first that they intersect at around negative 1. Well, in fact, it happens at negative 0.857. If I rounded to 3 significant figures, always at least 3, right? And then y is equal to 0.552. And there's another point of intersection. Let's find it. Second trace intersect. First curve, yes. Second curve, yes. It looks to me like they intersect at around x equals 2, so that's my guess. And in fact, it's 1.77 and 3.41. Write down the maximum value of the quadratic function. So let's find second trace maximum, option 4. We don't want to be doing y1, that is not the curve I'm using, so let's press down until the curve that we want to find the maximum of does appear. Now that this curve is selected, we're ready to choose the left bound. I'll move my cursor to the left, I'll move my cursor to the right bound, and then I'll stick it as close as I can to where I believe the max to be, and the max occurs. Now we need to interpret our calculator here. This obviously is an x value of 1. So our vertex occurs at 1 comma 4. But note the question, it says write down the maximum value. The word value means the y value only. Okay, if it said write down the coordinates of the maximum, well of course we need both the x and the y. But it wants just the maximum value, that's the y, so y is equal to 4 at the maximum. Now we need to use differential calculus to verify that the answer to E is correct. Differential calculus, if you think about what's going on, we've got some parabola, we know that we want to find the location of the maximum, we know that a maximum is a stationary point, we know that at a stationary point the tangent slope is 0, and we know that the tangent slope is the derivative. So let's start by taking our function And let's differentiate it so we can come up with an expression, the derivative, which represents the gradient. The derivative of 3 is 0, the derivative of 2x is 2, the derivative of negative x squared is negative 2x. So that's an expression that represents the derivative. Now we know that the derivative equal to 0 represents a horizontal tangent line which shows where the stationary points are. So let's set the derivative equal to 0 and find out what the x-coordinate is. Where does that occur? It occurs when x is equal to 1. But we're trying to find the maximum value. We need to find the corresponding y-coordinate. So let's substitute x equals 1 into the original function to find out what the corresponding coordinate is. And we end up indeed getting 4. There's actually one thing I haven't done here, and I'm looking at this, this is worth 5 points. I'm a little worried I haven't done 5 points worth of work, and I have a feeling I know why. At this stage I've only identified my stationary point, but I haven't definitively demonstrated that it is a maximum. To do this I need to do a first derivative test. So let's put our stationary point down on our number line, and then we're going to test some value over here, like maybe 0, and we'll test some value over here, maybe 2, and we'll substitute those values into the derivative expression to find out if the derivative is positive or negative, meaning that the function is increasing or if the function is decreasing. If I substitute in 0 into my derivative, I get 2 minus 0, that equals 2, that is a positive value. If I substitute in a test value on this side of the stationary point, like 2, I get 2 minus 4, that's negative 2, that is a negative value. So clearly our function was positive, it was increasing, and then at the stationary point it was flat, and then over here it was decreasing, demonstrating that 1, 4 is indeed a maximum, and your maximum value then is 4. Let's move on to number 2. You need to write down the value of y when x is 2. That's just a substitution game. So y is equal to 2 to the power of 3 plus 3 over 2, 2 squared, minus 6 times 2, minus 2. Now, I have a feeling that, yes indeed, look at part B, I'm going to end up having to sketch it. So perhaps straight away I should put it into my y equals. I'll clear the old ones. I don't know why the second one is not clearing. There we go. Alright, so I've got x cubed plus 3 over 2 x squared minus 6x minus 2. And it tells us what the window is going to be, so I'm just going to set this window up straight away. Negative 4 to 3. And from y, my y's are already good to go. So let's just have a quick look at the picture. Yeah, no surprise, we've studied cubics. We know that this cubic is going to rise at the right because the leading coefficient is positive. And we know that because it's a cubic, degree of 3, it will have 2 u-turns, always one less than the degree. So no big surprise over how this looks. It's an odd-degreed function, a cubic, which means that the end behavior is opposite. So anyway, the reason I've done this is because it's a lot quicker, I think, to find the value of y when x is 2 by saying second calc, and you can see that number 1 is value. Let's find out what is the value of the function when x is equal to 2. And your calculator tells you that y is 0 at that point. Okay? I could also have looked at table, second graph at the table, and here you can see that when x is 2, your y is equal to 0. So no matter how you do it, you should end up getting 0 as a result. Part I, we need to write down the coordinates of the point where the curve intercepts the y-axis. The y-intercept is the place when x equals 0. You can see on your table that when x is 0, y is equal to negative 2. So when x is 0, y equals negative 2. Look, it's asking for the coordinates this time. Part B, let's sketch the curve from negative 4 to 3. I've set up my graph with a width of 14 units because there's actually a width of 7. I just decided to make each one worth 2 units in width. And negative 10 up to positive 10, that's a width of 20, and so I've created 20 squares tall. And so Let me just work this out. That's my negative 10. That's my positive 10. I'm just locating my x-axis right now. Wow, this is tough resolution. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm guessing a little bit, but I think it's along there. And then my y-axis, 1, 2, 3, goes from negative 3 up to negative 4, sorry, up to positive 3. There's my y-axis. Okay, now I've set up my, oh, by the way, I didn't use a ruler. That's very bad form. Please use a ruler when making your axes. IB can be funny about that too. Alright, now, because I've already got my table, I can just put in these coordinates then. So when x is negative 4, y is negative 18. Well, I don't know how they expect us to graph that. That's off the window that they gave us. So I can't do that point, can I? Let's do the next one then. X is negative 3 and y is 2.5. So 2.5. It's about here. When x is negative 2, y is 8. When x is negative 1, y is 4.5. When x is 0, y is 2. I don't think I graphed the previous one right. Let me just move it. I think I put it at 3.5. It should now be at 4.5. That's better. When x is 1, we're now at oh, I've done my y wrong. It should be 0, negative 2. Shouldn't it? Sorry. Negative 2. There. When we're at 1, we're at negative 1.5, negative 5.5. When we're at 2, we're back to 0. And when we're at 3, we're at 20.5. Wow, we're off again. I don't really know how they expect us to graph this with such a limited y domain. So anyway, we go off the graph, and then through the points, and then off the graph again. There's nothing we can do about it. So that's a picture of our function. Indeed, if you graphed it, I hope we get, yeah, look, we could get basically the same thing, don't we? Dimensions are a little bit different, scale's different, but it's same points. We need to indicate the information that we found in part A, so we had the y-intercept right here. Let's label its coordinates, 0, negative 2. And we also need to write down the value of y when x equals 2. So when x is 2, we know that the y value is 0. We already found that one, 2, 0. So we've indicated that information. We're ready to move on to part C. Let's find the derivative of the function. Well, I need to look at it to see that. Okay, so the derivative of x cubed is 3x squared. Tell you what, I'm just going to recopy the function on the next slide. It'll be easier for me. So I've got x cubed plus 3 over 2x squared minus 6x minus 2, I think is right. Yes. Alright, let's differentiate it. Yeah, don't forget this notation right here simply means find the derivative. It's just expressed as a rate of change, but it's a different notation for y prime. So we'll find the derivative equals 3x squared. Now this 3 over 2 hangs out in front, and then we'll differentiate the x squared. And then the derivative of negative 6x is minus 6, and the derivative of the constant disappears. We can simplify this slightly now if you ever have trouble multiplying a fraction by something that's not a fraction, just turn them both into fractions. This is like the thing that's not a fraction, just stick it over 1, and then you'll remember how it's done. So we got 3x squared. When you multiply fractions, we multiply the tops, and we multiply the bottoms. So we've got 6x over 2, and that simplifies to 3x. Okay? Alright, part D. Let line 1 be the tangent to the curve at x equals 2, and let line 2 be a tangent to the curve parallel to line 1. We first need to show that the gradient of line 1 is equal to 12. Well, we know that the derivative is 3x squared plus 3x minus 6, and the derivative represents the slope, or the gradient, of a tangent. So if the slope should be 12, let's find out if that's true when we put in an x equals 2 into our derivative function to find out what the corresponding slope value is. Let's see what we get. 3 times 4 plus 6 minus 6, those cancel, and yay, we get 12 as required. Please notice that when it was a show that question, I did not use my given value anywhere in my solution. That was the final thing that got written. But that 12 should not appear before the very, very last thing that you write in a show that question. Part I, find the x-coordinate of the point at which line 2 and the curve meet. Alright, well line 2 is a tangent to the curve and it is parallel to line 1. So in line 2, we know that the slope must also be 12, right? Because if line 1 and line 2 are parallel, they must have the same gradient. So we've got its slope. I would love to be able to find out another piece of information. If I had a point on that line, then I could come up with that line's equation, couldn't I? How do I find a point on line 2? Oh, I see. Okay, if the gradient is equal to 12, why don't we set y prime equal to 12? Our slope is 12, so y prime is 12. And let's solve for the values of x at which this occurs. Quickest way to do this is probably to stick that into the calculator. And so let's put these in. We've got 12, and we've got 3x squared plus 3x minus 6. I'm going to deselect y1, which is our original curve, but we're not using it right now. Let's have a look at the graph. So that's the graph of the derivative. Oh, of course, I can't see where it's equal to 12 because 12 doesn't quite fit onto my y-axis. Let's adjust the window momentarily and put the y-max up to, say, 13 so that our 12 does fit. Okay, yeah, there's the 12, the left-hand side of the equation, and there's the right-hand side of the equation. So I can see that my derivative is equal to my gradient of 12 right here and right here. Let's find those locations. Okay, we'll find out where they intersect. Yes, that's my first curve, that's my second curve. I'm going to guess that they intersect at -2. Actually, they intersect at -3. So x equals -3 is one of my values. And what's my other value? Second, calc, intersect. First curve, yes. Second curve, yes. I think they intersect at 3. Actually, they intersect at 2. And so my two values, which will solve this equation, are -3 and +2. You also, by the way, could have solved that by bringing everything to the same sides of the equation, getting a 0 on the other side, and then either factoring or using the quadratic formula. Now there's no surprise that the slope is 12 when x equals 2, because that's what happened in line 1, right? When x was 2, our slope was 12. So no big surprise. The one I'm interested in is this other one. There's another point, you see, and we can see that this other point where they intersect is going to be at -3. So that's the x-coordinate at which line 2 and the curve meet. If you're having some trouble kind of visualizing this, let me draw you another picture for a moment. So you remember that we showed that when x was equal to 2, let me use this for that. Let's see if this will, oh wait. Yeah, I'll try using this. So this red line I've just drawn, I'm trying to show is the tangent at that point x equals 2, and it's got a slope of around 12, and we found out that there's in fact another place where the slope is also 12. It's parallel, so I'm just sliding over the line, and that other place is at x equals -3. So that's a picture of what's just happened. We've got then, this was line 1, and this over here, the parallel one, is line 2, and the x-coordinate at which they touch is -3. And part III, sketch and label L1 and L2. Well, there you go, I just did it. So they've been labeled. Just another quick look at that. Line 1 on the right was tangent at the point x equals 2. And line 2 is parallel, also had a gradient of 12, and we discovered that the other place that our tangent, our derivative, is equal to 12 occurs at x equals negative 3, and so that's line 2. And the last slide deals with part E. It is known that dy over dx, which represents the slope or the gradient or the rate of change or the derivative, that is equal to 0, meaning increasing. We are increasing when x is less than negative 2 and when x is greater than b. Have a look. Yes, indeed, our function is increasing as x is less than negative 2. Now, when we hit negative 2, it looks like a stationary point, doesn't it? And then we were decreasing between negative 2 and, it looks like positive 1, doesn't it? And then after positive 1, we began increasing again. So the question is asking, after what value, x is greater than what value, are we now increasing again? Where else is our derivative going to be increasing, positive again? We can see that occurred at a value of 1. When x was greater than 1 was where our function started to increase again. We need to describe the behavior of the curve from negative 2 to positive 1, and if you look at the curve, we can see that in between negative 2 and positive 1, what is our curve doing? It is decreasing. That is the behavior of the curve, decreasing. And part III, write down the equation of the tangent to the curve at x equals negative 2. Now have a look at our diagram. X equals negative 2. This is not a point that we have been dealing with previously. This is a brand new point, and we're finding the tangent at that point. We need to find the equation of that tangent. So ignore line 1 and line 2. They're in the past. We're dealing with an x value of negative 2, and we're trying to find the equation of the tangent. We need two pieces of information. Let's find the slope, and let's find the point. To find the slope, we'll substitute the x value of negative 2 into the derivative function. So our derivative function was 3x squared plus 3x minus 6. So I've got 3x squared plus 3x minus 6. Okay, that gives me 3 times 4 is 12 minus 6 and equals 0. This is really no huge surprise that I got a slope of 0, because on my diagram it sure looks like my tangent slope is 0, doesn't it? And also, we've already made the assumption earlier on that because we were increasing up to negative 2 and then decreasing after negative 2, obviously at negative 2 that must have been a max. And if it's a max, it's a stationary point, and of course the derivative is 0. So that's going to make things much easier. Our slope is 0. If its slope is 0, we know that we've got a horizontal line, and we know that all horizontal lines have got the form y equals something. We also need a point. Let's substitute negative 2 into the original function. Quickest way to do that is just to look at my table again. Okay, so I'm looking at my table and I'm interested in y1. Looking at, it's deselected, sorry. Let's go back to y equals. I need to re-enable it. And let's just disable the others. I'm not interested in them anymore. And now let's look at the table. And what happens when x is negative 2? My corresponding y value is 8. So I've got this horizontal line that is going through this point, negative 2, 8. What is the y value equal to? Obviously it's 8 for every point along the line. And because it's a horizontal line, that is the form of the equation of the tangent at that maximum point, x equals negative 2. Okay, that's everything for numbers 1 and 2. Next video we'll have a look at a couple more problems.